Right, welcome to the content that would have been on Wednesday, September 2nd and Labor Day, September 7th, and probably going into the 9th as well. Alright, so this is basically the rest of kinetics. So I got two slides of what the objectives are, so use this as a checklist. We're going to understand and be able to calculate how concentrations change with time. You're going to learn about first and second order reactions, what that means, and how to distinguish between the two. You're going to be able to evaluate the concentration of a certain reaction component at a certain time based on order and initial concentrations. And you're going to be able to calculate and evaluate something called a half-life. And we're going to talk more along how reaction rates vary with temperature, how they vary with temperature, and we're going to predict the overall rate laws from a mechanism, and before that you will learn what a mechanism is, and talk about intermediates and catalysts. Alright, so first order of business is how to calculate the change in concentration of something with respect to time. And this is something we actually haven't really messed around with at this point. So what we did know, what we have figured out is a way to describe the rate of a reaction and describe it in terms of changes of concentrations in components. Now, in case you haven't seen this before, and we're switching into more calculus notation here. Previously we talked about changes as these deltas. Now when we're talking about infinitesimal changes, the mathematicians switched to these d's, which I'm going to do. We developed a formalism that allowed us to describe the rate of a reaction in terms of the concentration changes. And this formalism of putting a negative sign in front of the reactants and dividing by the coefficient to make sure that we get the same actual rate regardless of which species we use. So the question we're going to ask here is, so we developed this thing called a rate law, which told us what the rate of a reaction would be with any particular set of concentrations. Now what we're doing is we're going to assess how does the concentration of any one component, A, B, or C, actually change with time? And the answer is, it depends. And specifically, it depends on the rate law. And that is because the rate of the reaction is constantly changing because remember, the rate laws were something like, it could be K equals A to the first power. It could be K equals something to, to the second power, something like that. So this is, this can look like a fairly daunting thing because the rate of the reaction is constantly changing because the concentration of the reaction components are constantly changing. But it turns out that with calculus, this is actually a fairly simple thing to figure out, which is what we're going to do. Now, if you are not yet in calculus, fret not. All you need to know actually is just the end result, which will hopefully be clear from the next couple slides. All right, so let's talk about our generic A going to B and 2C. So we can say that the rate of this reaction, and typically we tend to use reactants in these discussions, is equal to negative change in concentration of A divided by the change in time. And if it's a first order reaction, this is equal to the rate constant K times A to the first power. Again, remember, in the rate laws, usually only reactants show up in here. Now this means that this reaction is first order with respect to A. And since A is the only reactant, and by extension the only term in the rate law, it's first order overall. And this turns out to be the simplest case. And so keep in mind rate constants, these k's here, are independent of time. That's why we call them a constant. But the rate actually is not, because the rate will change with time, and more specifically, it will constantly slow down because these concentrations are dropping. And so the question is, how can we calculate the concentration of A at some given time?